So welcome to our colloquium. So today's speaker is Tobias Micklitz from CBPF. He's visiting us from last Wednesday, right? Yeah, and he will stay until tomorrow. So as usual, I introduce briefly the speaker. So he got his PhD in Cologne in 2007. His advisor was Alex Altran, that is a friend here. Then he spent 2 years in Argonne National Lab. Then he moved back to Germany in University in Berlin with an assistant professor positions. And finally, in 2013, he joined CBPF, and he's there from that time. So his topics are, let's say, about quantum chaos and many-body physics. And indeed, today he's going to talk about something related to that, and he's going to talk about the emergence of the Fermi-Golden's rule. Tobias?
Okay,
yeah.
So first of all, thanks, Dario, for the invitation. So it's great to be here, very interesting time so far. So yeah, I'm going to talk about the emergence of Fermi's golden rule, which is a work that was done in collaboration with Alan Morningstar and David Hughes from Princeton and Alex Altman from Cologne. So I'll first briefly recall Fermi's golden rule, and then I'll actually talk about more general. So Fermi's golden rule is about the decay of, let's say, two-level system, in the simplest case, to some bath, which in the simplest case is just has a continuum final states. So here we want to talk a little bit about what happens if you decay into what we call an imperfect bath. Specifically, we'll be concerned if the bath consists of a discrete set of states. But I'll put this into a more broader context and talk a little bit about thermalization in closed many-body systems, so to make the context a little bit broader, but I have to be a little bit careful. I should make a disclaimer here, because in the end, the problem that we'll talk about will be much simpler than really many-body localization. So I hope not to raise there too many expectations. It's a very hard problem, many-body localization. I don't have much to say about that, but a much simpler problem, which is then the emergence of Fermi's golden rule. Yeah. So then, yeah, this paper is can find here, and so let's start with the simplest case where you have, let's say, a two-level system weakly coupled to some bath, and then the probability to stay in the excited state is exponentially decaying with a rate which in the weak coupling limit is given by Fermi's golden rule rate expressed here, and as already said, so the usual context where one studies this is where one has a continuum final states. Like, let's say you have an atom which is in excited states and goes to the ground state by emitting a photon which can propagate in any direction, so you have a continuum final states. Recently, we are actually much interested in what happens if you have closed many-body systems, so where you have, let's say, the ideal or the limit of an idealized situation where you have a well-defined many-body system consisting of 10 to 100 whatever degrees of freedom, which are, however, very well separated from the environment. So where you can really think about this closed many-body system decoupled from the environment. And an interesting question, or a very challenging question, that then comes up in this scenario is when actually this closed many-body system acts as a bath to its constituents. So in principle, you can think about two possible scenarios. So in the one case, you can think that, well, you have many-body system, so you have interactions, so the interactions will lead to some ergodic phase in the sense of an ETH, eigenstate thermalization hypothesis, such that you can calculate, for example, expectation values of local operators in a given eigenstate just by some statistical ensembles. And what is behind there is, well, because you have interactions, there's extensive entanglement in the system. So typically, if this holds, then you have volume law for entanglement entropy, and the mechanism that drives this entanglement is chaotic dynamics. So you have information scrambling and just chaos that leads to this entanglement and in the end to some ergodic phase. You can also think at least of the complementary scenario where the system actually does not thermalize in the sense that it becomes ergodic, so that the eigenstate thermalization hypothesis does not hold. So this implies then that you have low entanglement, so typically you will have then an area law entanglement, and this is of course important if you also think practically you want to store local information, you don't want to have a lot of information scrambling going on. So this is a question which is like, I would say, of very much fundamental interest, but also of practical relevance. So specifically, if we think about like quantum computers, like it has been pointed out that for example, the Transmont platform for quantum computers is actually very close or dangerously close operating to quantum chaos. So you have to understand really well under which conditions these close many-body systems actually lead to chaotic dynamics also for applications. So to put this question in a more condensed matter context, you can think about it differently. So consider, like the standard example here would be to consider a low-dimensional system of electrons which can interact with some local disorder. So you have some imperfections where electrons can scatter off, and you have electron-electron interactions. And again, let's consider the situation where we are in the idealized limit where the electrons do not act with any other degree of freedom, like with phonons or anything. So there's no external bath where the system couples to. And then we can ask, so we have these electrons, let's say in this box here, decoupled from the remaining world. They can scatter from static disorder and they will interact. And then you can ask, well, what happens if I make a measurement of transport? Is this device now transporting current, yes or no? And to understand like this question a little bit better, we can first look at the limit where we don't have any electron interactions, because there it is known that actually in low dimensions the impurities, the scattering from impurities has quite a drastic effect on transport. So at short time scales you will have just diffusion, but then since, I mean, your electrons here have quantum mechanical wave nature, there will be from the scattering just a lot of quantum interference going on. And if you go to longer and longer timescales, these quantum interference processes accumulate to actually stop diffusion, and the single particle wave functions in this low-dimensional disordered systems without interactions are just localized. So this is the famous Anderson insulating. The system would be an insulator at long-length scales. So then you can ask what happens if you now turn on the electron-electron interactions. So if you are at zero temperature, then everything that has been said just simply applies because the quantum interference is still fully there. So at zero temperature, you don't have any inelastic scattering or real processes that can actually lead to decoherence. So the quantum interference is just fully still in the problem, meaning that at zero temperature, you will expect that you still have an insulator. Now, in the opposite limit where you have high temperatures, well, there will be a lot of inelastic scattering going on, so there will be a lot of source for dephasing, so the decoherence will eventually kill the quantum interference underlying this insulating phase here. So at large temperatures, for sure, there will be just diffusive transport. And the question then on having a thermal or non-thermal phase is actually how you should now think to connect these two limits. So is it that there is actually a critical temperature up to which the conductivity remains zero, and only at some finite temperature you will have finite transport? Or is it that at any finite temperature, immediately the conductivity will be finite? So this is equivalent to the question if these localized, single particle localized states, once you turn on interactions and finite temperature, will they provide a bath for themselves to actually thermalize, yes or not? So this has been actually a long question around, like for many decades, I would say. And there has been some breakthrough progress in 2006 by the work by Pasqualene and Altschuler, which in a way started this new wave on it's called...
So you have periodic boundary conditions, or how do you keep it not interacting with the boundary?
No, you have like boundary, but just like reflection, or you can have periodic boundary condition. Doesn't matter so much. The important thing is only that you do not have like a bath that you can dissipate into. Like there's no source for decoherence.
But as you take the infinite volume limit, the properties stay the same?
Yes.
I see.
Yes.
And what do you mean by low dimension? Sorry.
Oh, no, it's like a two-dimensional or quasi-one-dimensional system. So it's just because Anderson localization relies on the quantum interference processes, which are, like if you have return loops, you have a lot of quantum interference that will drive endless localization, and the return probability is higher in the lower dimension you have. So in two-dimensional systems or quasi-1D, actually, the single particle system is always endless and localized. So, yeah. So, so there had been this, let's say, major breakthrough by the work by Basker, Alena, and Altschuler, which actually gave an very convincing arguments that the answer to the question posed on the previous slide is actually the first case. So there is a critical temperature Tc up to which the transport is zero, meaning up to which actually now your system is in this insulating regime, and only then you make the transition into the thermal phase. Now, after this work has inspired many other works on different systems, which then show the same features. So specifically what has been studied a lot is these like 1D spin chains, where you have next nearest neighbor, spin interaction, then you add like your disorder, some local magnetic field, which is like random. And in this system, then it is also important, like you can study again this transition from localization to delocalization, now driven by the disorder strength. So importantly, you can study the system now, let's say, in the infinite temperature limit. So you're not interested in ground states of this problem. So you're really interested in generic states. So you can have a finite spectrum. So you can just look at the infinite temperature limit and then see what happens as you crank up this disorder in terms of this random magnetic field. And the prediction is that, again, you will have at low disorder, well, you have just what you expect, the usual thermal phase where the system provides its own bath. But as you crank up disorder, you make the transition into this many-body localized phase, which is now for generic states at a critical disorder strength, which you have to pass to make. Now this kind of systems have then been studied a lot also numerically. I mean, it's very hard to make progress in analytics, so there has been a lot of numerical activities which exactly show what you expect here. So you have some indicators from the, let's say, spectral correlations, which show that generic states, as you increase the disorder strengths, make a transition from localized to from delocalized to localized states. So this has been a lot of activity, and everything looked quite promising, maybe until whatever. 5 years ago, when people started actually first looking closer into this numerics, and then also there's some question about, there's major analytic work, there's also some doubts about these systems. But the main observation here is actually, so carefully looking, for example, at the numerical data, it became clear that the critical disorder strengths that you need to make this transition keeps growing as you increase the system size. And actually there's a claim that if you very carefully make the analysis, then you will see that the disorder strength actually scales with the system size, meaning that you need extensive disorder to really make the transition. So in the thermodynamic limit, this is not a realistic scenario. So all this many-body localization phase should actually not exist. So this is, as said, a very tough problem with open questions, so it's not so clear what really the situation is. So the previous analytic work also missed some subtle correlations. So it's not so clear what the status is. And the question just prevails if many-body localization exists or not. Another mechanism that is also relevant is you have to think about rare events that can actually destabilize the localized phase. So even if you think you're in a localized phase, it may be that rare events will just drive transition into a thermal phase. So to explain this a little bit, let's think about the following scenario, that we have a 1D system, and we think we prepare the 1D system such that we are expected to be in the localized phase. So then we can think of our 1D system just as a succession of regions, alternating regions, which are thermal, like small thermal regions, which are in between. There's insulating region and there's a small insertion of thermal regions. Now these small segments can be just randomly distributed, like their lengths, with length scale they can be randomly distributed with varying lengths. However, if we are assuming that we are in the localized regime, then the average size of the insulating regimes should be much larger. So let's assume that we somehow randomly draw our length scales from some distributions where the average value of insulating regimes is much larger than thermal, so you will end up with such a configuration, and you think, well, if the insulating regimes are much larger, probably this is like in an insulating or minimal localized phase. So the point made here is that, yes, you could think so, but since you're drawing randomly your lengths, there can be rare events where actually your insulating regimes separating two thermal regions happens to be very small, just because of a rare event. And what happens then is that these two thermal regions can actually, let's say, propagate information through the small insulating region because it's very small. And in this way, actually, these thermal regions can thermalize this very small insulating region. What will happen then is this thermal region will grow in size, and this larger thermal region can then start thermalizing more and more insulating blocks. In this way, it like you create by a rare event, you create this avalanche where then the bath will just start by some rare region, but it will just propagate through the entire system and destabilize what you actually thought to be an insulating phase. So this has been studied in a very nice phenomenological work by some strong disorder randomization group techniques, where you just randomly draw these length scales from the thermal and insulating blocks from some distributions, and you do some phenomenological RG scheme which tells you how to renormalize these distributions or as you do some coarse graining. An important ingredient in this like phenomenological work is that you have to realize that there is a strong asymmetry in the problem, because if you, for example, consider such an insulating regime or an insulating block sandwiched between two thermal blocks, then actually let's say the time to hybridize through the insulating block is exponentially large in the length of the thermal block. While when you have the opposite case, where you have, let's say, a thermal region sandwiched between two insulating blocks, well, information can just propagate much faster, so it's not exponentially long time, but it will be just an algebraically long time. So there's an asymmetry in the problem, which they implemented by hand into this phenomenology RG, and what they then derived is like the RG equations from which they found the fixed point distributions at the critical, like at the transition, which then share this characteristic of having a strong asymmetry, meaning that the fixed point distribution of insulating blocks is an exponential function, while the thermal is an algebraic function. Is interestingly then the prediction of this simple or toy model is that the transition driven by avalanches is of the Kosterlitz-Thouless type, which is quite interesting. For example, if you then look at the critical point, it just shares the characteristics of the localized phase, like in a superfluid, in a Kosterlitz-Thouless transition, the critical point is also superfluid. So there's interesting consequence from this. Now, a different way to look at this avalanche mechanism, which takes more into account like what we're interested in, this discrete bath, is to consider this so-called quantum sun model, where you have a large thermal region to which then isolated spins couple. So you can model this thermal region here by some random matrix Hamiltonian, then couple like isolated spins to this bath. So the spins do not talk to each other, they just couple to the bath, and then you can organize actually this system here in a decreasing order of coupling strengths. So this would be the strongly coupled spin and the next strong coupled spin and so on. So you have here your random matrix Hamiltonian, and you have these chain of spins that all couple only to the bath in a decreasing form of coupling constants. Now, naively, you can now ask, well, what is the probability that this outermost spin will just thermalize with the bath? And said, like naively, you would think that, well, the information, like for the hybridization time or to propagate information through the system, will exponentially depend on the distance. However, an important thing is to take into account in this problem, how do you go back? Foi, desculpa. An important thing here to take into account is the feedback mechanism. So let's consider let's say the first spin here that is strongly coupled. So you can just, by simple Fermi's golden rule argument, say, well, this spin here thermalizes with your bath if the Fermi's golden rule decay rate, so which is the level broadening, is larger than the mean level spacing in the dot. Then you have a lot of, let's say, states to couple to, and you will just thermalize with the system. Now, the feedback mechanism is, if you ask now the same question for the next spin, you have to account for the fact that the first spin actually was integrated into the bath, meaning that the mean level spacing of the bath by inclusion of the one spin just decreased, and this now allows you to actually thermalize the next spin, which may have a weaker coupling, because the first spin was included into the bath, so the mean level spacing was reduced. In this way, you should work your way through accounting for this feedback mechanism that as the bath grows, well, the level spacing decreases and can more and more thermalize things, right? So this then is like the motivation to think about like what we wanted to do is just really the simplest case. Imagine that you study like the Fermi's golden rule, where you have a level that is coupled now not to an infinite bath, but just to a finite size system, meaning that there you have a finite level spacing, and see how the finite level spacing affects like the decay, and how like the bath itself has phase coherence, so how the phase coherence affects the bath. So we really want to make a step back, and I don't have anything to say about many-mode localization problem, which is a much harder problem, so I'm really talking about a very simple problem, which is the single level coupled to a finite bath, finite level spacing, and fully phase coherent. So what we wanted to understand is what kind of information, like the spectral correlations and the wave function statistics, whatever, how do they affect the decay? And well, it's a very, like in a way, simple, more like textbook problem. So we were surprised that this hadn't been done like in this way, what we were doing. So we want to see what happens to Fermi's golden rule if the set of finite state is discrete. Yeah. So the model that we have is a simple model. So we take a Hamiltonian where we have the single level, epsilon 0, which is now coupled to this bath, which we model by a random matrix. And we take a coupling which is just consists of also random matrices. And as said already several times, well, the important thing is that we have here a large number of discrete sets. And the important parameters, so we have the random matrix Hamiltonian, which will have a bandwidth lambda, and you have n states. And the coupling here of the single level to the random matrix is now reduced by a factor g. So if g equals 1, this would be just one n plus 1 dimensional large random matrix, but we make this coupling here much weaker, and this will then be like we want to see what happens like in what be the Fermi's golden rule regime where the coupling is weak. So what we calculate is just the probability that you will remain in the single level after time t. And this probability is then averaged over various realizations of the random Hamiltonians. And well, an important time scale, since we have a finite bath, means that we have a bandwidth lambda, we have n levels, so we have a mean level spacing, which is a ratio of lambda and n, which means that we have now a characteristic time scale due to the finite level spacing, which is the Heisenberg time. So if we have time scales larger than the Heisenberg time, we should see at least that, I mean, we have a finite discrete set of levels in the system. And yeah, so let's see, like, what would you expect first? Well, you expect, like, from Fermi's golden rule, you have exponential decay by a rate which now is just given by the bandwidth of the RMT system, but reduced with a factor g, right? So if you would have just a full RMT, it would be given by the bandwidth, but now you can play with this parameter g to make a weak coupling. And of course, very naively would say Fermi's golden rule in the infinite time limit, the probability goes to 0, but of course you have a finite size system, so this should not go to 0, but to some finite value. So to understand this finite value, we can just simply think in the way that the Fermi's golden rule rate introduces a level broadening, which then means that you have the level broadening divided by the level spacing, number of levels the one level here couples to, which it will thermalize. So this will be our interesting parameter. So G can be very small, but N can be very large, such that you still have a large number of levels to couple to. So with this parameter, which is, let's say, the effective dimension of the system where you couple to, we can consider various regimes that we expect. So in the limit where G goes to 0, well, you don't have any level on average you couple to, and the probability will just remain 1. In the opposite limit where G equals 1, you just have one big random matrix Hamiltonian, so the probability to remain in the one level is just given by 1 over n, the number of levels that you have. And Fermi's golden rule regime should apply when the coupling is weak, but you still have a lot of levels to couple to. So let's call gamma, actually this would be 2 gamma, is the number of levels that you couple to, and this would be like the Fermi's golden rule regime. Now, just a technical remark is, so we do the calculations with help of like Yefitov's supersymmetry method. So let me just give a very brief, I mean, so who's not interested in technical details can just forget about it, but maybe it's interesting to see this method, because I mean, supersymmetry seems fancy, but it's just a very more technical, simple way how it appears. So let me just try to explain this briefly. So this is like a typical observable, like here this would be the probability to remain in a given state, or yeah, in this given state. So typical observable will be given by a product of resolvents of your Hamiltonian, a retarded and advanced one. So this is like a retarded advanced Green's function, their product is some probability. So let's consider the simple case where our Hamiltonian is just one big random matrix. So we want to calculate this, and the trick to do this calculation is to write down some generating function, which is just the ratio of determinants. So important point here is we have like a probability which contains a retarded and advanced component, so there will be one energy will be slightly retarded, one be slightly advanced, and we can generate these kind of observables from ratios of determinants where some of these energy arguments are slightly shifted in the positive and some in the negative complex half plane. And then the basic idea, this is now our poor man supersymmetry of condensed matter physics, is, well, we introduce fermion and bosonic variables to express the ratio of determinants. So that's how the supersymmetry enters. Then we have a representation of this generating function in terms of the Hamiltonian, which we can easily average over, let's say, Gaussian ensemble. And then we do the usual things that we decouple in the relative degree of freedom, integrate out the microscopic degrees of freedom, and write down an effective theory in terms of this microscopic, this effective degree of freedom, which now here, interestingly, is a degree of freedom which is like singlet in the Hilbert space. It doesn't have any structure, meaning that the effective theory will then have the large parameter n here appearing, because this is like doesn't depend on the Hilbert space, and it's just a matrix in this, let's say, internal space of retarded and advanced components and Bose Fermi components. And this large n then invites to do a saddle point approximation. So subjecting this to a saddle point approximation, you will find a solution which has some symmetry breaking. So you see in this effective theory, you should think of this I lambda q as some effective decay rate, or some imaginary part that enters here, which now will enter with opposite sign in the retarded and advanced component. So if you do a saddle point analysis, you should think of this Q here like as a self-consistent Born approximation self-energy, which will have different signatures in the retarded and advanced component. So your saddle point will have some symmetry breaking this retarded advanced sector. And then you have soft rotations around the sector because it's only small energy arguments which will spoil the symmetry. And then you can derive a soft mode action, which is then, like we would say, the generic model for quantum chaos. So that is the effective action that encodes all the information on spectral correlation and so on quantum chaos. So that's our universal theory of quantum chaos. And this is quite interesting. So this D you should think of like this energy difference divided by the level spacing. So it's in a way the conjugate of the time scale at which you look at the problem. So if you look at time scales much smaller than the Heisenberg time, this Z over delta will be a large number, and you can just do perturbation theory and quadratic expansion here. will just have a propagator, which is just a zero-dimensional diffusion operator, right? Diffusion mode. And now, as you go to longer and longer timescales, you will have interaction between these diffusion modes, which will just describe quantum interference processes. And once you come to the order of the Heisenberg time, this parameter is not large anymore. You enter into a non-perturbative regime and have to integrate really over your entire soft mode manifold. And this is where the supersymmetry is very convenient, because you can just do these calculations oftenly just exactly, because you can parameterize in these manifolds and just solve integrals. So now in our problem, what we actually do is we model our system by two quantum dots of different size, which we then weakly couple. So now, hopefully, this is understandable. This would be like the universal series of quantum chaos for the decoupled systems. And then you have some coupling matrix, which actually wants to lock these degrees of freedom onto a single mode. So you want to somehow make a strong coupling, meaning that if the coupling is strong, these independent degrees of freedom get locked to a common mode, which means that this entire system is described by a single then mode, which describes quantum chaos of the entire system.
Sorry, I'm a bit confused. What you call Q2 is the two levels, is the...
So what we do here is actually a different calculation. We say, let's take two dots of different sizes, which are both described by our random matrix.
So this is more general than
yeah, it's more general. So we just do it more general, and then...
Yeah,
So that's like the machinery that we apply to then calculate like our probability of residence by these integrals. So then let me turn to the results. So the first thing that you can do with these techniques is calculate the probability of residence in the infinite time limit. So this is like as what you would expect. So you can derive some exact expression as a function now of, this is our relevant parameter, the gamma, which is the number, effective number of levels that you couple to. So this is now in the limit where you really take one level coupled to. So as a function of this gamma, you see you make what you expect. Well, if gamma is much smaller than 1, you don't couple to any level. The probability of residence will remain close to 1. It makes the transition to 1 over n, or 1 over n plus 1, as you would expect. And at the order of let's say, what is this, 10 here, you recover what you would expect like from a simple Fermi's golden rule like regime. You have many levels you couple to, even if the coupling is weak, and the probability of resonance is just 1 over the number of levels that you couple to, so it's 1 over gamma, right? So yeah, so this is just describes like now all our different regimes, and now we can look at the probability of residence at finite time in these different regimes. So let's first look at the regime where we have weak coupling. So let's take 2 points where we are still not what we would call the Fermi's golden rule regime, and see how the probability of residence evolves in time. So this is now like you can, or we didn't manage to write a full closed nice formula, so there's still some integrals involved in this probability of residence, but this you can calculate then on the computer and compare to numerics. So this is now 2 couplings where you're still not in what we would call the Fermi's golden rule regime, so where the probability of residence is still not given by 1 over, in the infinite time limit, is not given by 1 over the number of levels you couple to. And you see this is the weaker coupling, this is a stronger coupling, and for us, at least in the beginning, surprisingly, well, initially you have the exponential decay, what you would expect, but then there is a non-monotonous behavior. So the probability goes down, and then at some point it just goes up before it saturates to some finite value. So at least in the beginning it was surprising that the probability is not monotonous. And you see that actually then you have an increase here to some plateau, and this becomes more and more pronounced if you go to stronger coupling. So that's something that we observe in the weak coupling limit. Now you can look at the same probability as a function of time in the Fermi's golden rule regime, and you see that the coupling this non-monotonous increase really becomes just exactly like this ramp and plateau behavior. So in the Fermi's golden rule regime, where you have a lot of levels to couple to, you can actually then calculate this probably exactly, so you can resolve these integrals, and you find that you have the exponential decay like the usual Fermi's golden rule, that you expect at short times. Then you have a minimum value here, which is 1/2 gamma. So 2 gamma is really the number of levels that you couple to. And then as you increase in time, you have this linear ramp. So the probability increases linearly up to the Heisenberg time when it saturates to a plateau value. And actually, if you look at this, so for people from quantum chaos, this immediately rings a bell. Like if you see this exponential decay, linear ramp, and saturation behavior, well, this is exactly what we know happens in this random matrix series of unitary of the unitary ensemble for the spectral form factor. So this is now the Fourier transform of the level correlation function. So quantum chaos has this characteristics that level have this Wigner-Dyson statistics, which says that levels repel each other. So that's the characteristic of chaos. And this level repulsion reflects exactly in this spectral form factor, which has this initial decay, and then you have this linear ramp and the saturation behavior. And this linear ramp you can understand diagrammatically. Like if you think about this diffusion modes, you have to calculate such a diagram where you have some sliding symmetry in time, which just guarantees that you have this initial linear increase in the spectral form factor before you saturate. So indeed, if we look in the perturbative regime, we can, by diagrammatics, see then that the probability of resonance in our problem has these 3 contributions, one of which turns out to be the spectral form factor. So at short times where we can do perturbation theories, we can actually calculate the probability perturbatively. We have first the Fermi's golden rule, let's say incoherent decay. This saturates to a value which is 1 over the classical return probability, which is 1/2 gamma, which you would expect. And then what will just happen is that because you have fully coherent baths, you will have quantum interference correction to the classical return probability. So this is just like the usual Fermi's golden rule decay. Now you decay into a finite system, so at long times you will expect that the probability that you remain in the one level is just given by 1 over the number of levels that you couple to, so that's the return probability. But since you now have a phase coherent bath, there's quantum interference corrections to the classical return probability, which turns out to be exactly described by the spectral form factor. So this now then allows you to actually make some guess about different types of baths. So far we have considered the simplest case where our bath is described by some random matrix without any symmetry, so it's just a random Hermitian matrix. But if you have time versus symmetry, you have some constraints on the matrix. So there's this famous Wigner-Dyson classes for let's say generic systems which are not superconducting. In condensed matter, you distinguish between systems that don't have any time versus symmetry. Then if you have time versus symmetry, you can have 2 cases. One is that time versus symmetry comes with a spin rotation symmetry. In this case, you can think of your Hamiltonian as 2 blocks for spin up and spin down. They completely couple. And you can think of a scenario where you have time versus symmetry in combination with a broken spin rotation symmetry, where you have a different kind of matrix. So in the simplest case we considered so far, the entries of the matrix are just complex numbers. If you have time versus symmetry in combination with spin rotation symmetry, it's just real numbers. If you have time versus symmetry but break spin rotation symmetry, you can parameterize these by some quaternions. So then, based on what we learned so far, we can make them some educated guess if we change now our baths to have time versus symmetry. So what we need to make our guess is several ingredients. So first, well, there will be an exponential decay in the beginning. Then we should have a saturation value which has to do with the return probability, which so far was a return probability in a system without time versus symmetry. If you have time versus symmetry, well, then you enhance the return probability by some quantum interference effect, which is well known. And then what you also need is a spectral form factor in the 3 Wigner-Dyson classes, which will describe how the non-monotony then happens at larger times. So this linear ramp and plateaus for the unitary class, and the orthogonal classes is rounded, and in symplectic class one actually has this character spike at the Heisenberg time. So this is another ingredient, and then the final ingredient that you need to know is the long time plateau value that you expect to saturate to. This is just given by the wave function statistics, and again, like in the random unitary ensemble without time reverse symmetry, the eigenstates are, you can think of random complex vectors of random complex numbers. They become random vectors of random real numbers in presence of time reverse symmetry. So combining the information on the return probability, the spectral form factor, and the wave function statistics, you can make a guess on the decay or this probability of residence in the three Wigner-Dyson classes, and initial exponential decay that saturates at some minimum value, which has to do with the return probability, and then an increase by the spectral form factors and saturation value, which has to do with the wave function statistics. And then you can compare this guess to numerics, and it perfectly fits into this expectation. So then what we just did wanted to see, well, we have this like ideal bath of full random matrix, so how actually robust are these results? So you can think of now not having a fully chaotic system H, but you can include more and more symmetries into this bath, meaning that you can, like every symmetry allows you to block diagonalizes, and taking the extreme limit, where you, let's say, have an integrable bath, your random matrix of the bath will be just a random diagonal matrix. And then we just check that while, even if you have a like this integrable bath, due to the coupling to this one single level, these levels will all talk to each other. So if the coupling isn't too weak, this will then provide chaos in the bath, and all our results just simply apply, even in this case, simply because chaos is induced by the weak coupled level. So then maybe just the final thing. So this is all about, like the story that I actually wanted to tell for the very simple problem, right? A single level coupled to some chaotic bath, and it turns out that all the information on the bath, the level correlations and the spectral correlations and wave function statistics and so on, enters in this quantity. Now, of course, one can now try and make this problem more interesting. This is something that we are very much interested in, is like to try to extend these supersymmetry techniques now to the real interacting problems. So we are working a lot on trying to see how one can generalize these techniques to let's say, systems that you now really are interacting. So you have to look at tensor products of some systems. And a simple application you can think of is, for example, if your bath now is not a full random matrix, but it decays into segments, like the Hilbert space is a tensor product of subspaces, which are just weakly coupled. So you can think of that you have segments that barely talk to each other, and you have a very slow scrambling time that allows you to propagate information in this bath. And then you can think of a scenario where the scrambling time is so low that actually then this probability of decay will first see coupling to like this unentangled product of individual baths. So you will have some return probability which will have a peak, which is larger than in the fully equilibrium thermalized bath, and then as a function of the thermalization or the scrambling time, you should then decay in the long time into this. So that's something one can look at then, now trying to really go to the problem in the end that we wanted, which is the many-byte localization. So as said, yeah, the disclaimer is that the problem that I discussed, of course, is not the real true problem. It's a simpler problem, but I found it interesting in the sense that it turned out to be very rich. Okay, so this is then the conclusions. Discuss the decay into an imperfect bath, which here is the simplest case. Just what is the effect of having a finite level spacing, and the fact that the bath is phase coherent. And it turns out that the decay is not just a simple exponential decay, but it's non-monotonous. So you have this in the unitary class, at least this characteristic decay, dip, ramp, plateau structure. And it turns out that this structure knows about all the, let's say, ingredients from the bath, which is the level statistics, in terms of the spectral form factor, return probability, and the the wave function statistic which enters, and these actually holds under quite mild conditions, meaning that even if the Bath is not a fully random matrix, the coupling will typically induce chaos. And of course, the next step is what we are really working on is trying to see how to attack the true many-body problem. Yeah. So with this, I would like to thank also, so the agency point.
Okay, thank you very much. Questions?
So, is there a way to verify your results in an experiment?
Yeah, in an experiment, I mean, you should be able to. I mean, okay, you have to measure the probability to remain. I mean, yeah, I think yes. So you have to somehow isolate a single level, right, and then try to measure like the probability that initially preparing your initial state that you will remain in the state, right? But then you have to, yeah. I guess yes. The answer is yes. No, I don't know. So I don't know, for example, if so you have to go, now you have to think aloud really like a reasonable set of parameters. So we want to have a bath, so it shouldn't be too small, but we don't want to have the Heisenberg time to be very, very large, right? Because we have to have phase coherence on the time scale of the Heisenberg time to see this. So one then really has to study what is a reasonable, like you would have to make the bath as small as possible to have like short Heisenberg times to see the effect, but then have to see how all this applies. But I think it should be possible to see, yeah. Actually, I once talked at CBPF to like the NMR people, but yeah, I don't know if this is a realistic setup. Study it there, yeah.
Thanks, Tobias.
Yeah.
Is there any way to, instead of sampling random the Hamiltonian, rather sampling the random the change of basis? Because so if one samples random the Hamiltonian, the original, let's say, like is a little bit cheating.
Sorry, it is what?
It's a little bit cheating because one says, okay, I want to couple my system with a discrete energy spectrum.
Right.
But if I have a random matrix and I make many, let's say, average, at the end I will have a continuous spectrum. So it's like...
Well, you don't have a continuous... you have the Heisenberg time where all these effects appear, right? So you have to have finite level spacing.
And at the end, the spectrum for factor that appears is the one of RMT. So it's the universal, let's say.
Right.
So
you're right.
But the question was, if instead of modeling let's say the Hamiltonian as a random, you model this change of basis as a circular ensemble, do you think that the answer at the end will be the same?
Yes. So I mean, even like the question, like, so the question would be, how would you also model the coupling, right?
Yeah,
so if this is random matrices, you just induce, it's like universal.
No,
so,
no, I was thinking more in a more, let's say, quantum info perspective, because you see that if you have the time evolution operator, that is at the end what you need, you can model it as a byproduct of two random unitaries, and in the middle the energy, the fixed energy.
Yes.
So that will prove fixed energy without making the ensemble average over the whole
it
energy.
will not change. No.
Okay.
Yeah.
And the other question was, so you have, there was a point in which you coupled two sigma models?
Right, yes. So what we do, the calculation is more general. So instead of having one level, what we do is we have, again, like that's the simple scenario where we have two sigma models. So this is universal chaos, right? Which are now coupled by this coupling here. So that's again like the simple, because it's not in some tensor product, but it's like a non-intact problem. So sorry, you have to ask your question.
So in the first, you have two saddles separately per sigma model, right?
Yes.
So now you have like 4 saddles. How do you manage to...
but the saddles are not so. So the saddles are not so. Are not so important. So what you see here is like. So the Q matrix has this property that Q squared is 1, right? Because it's rotation around some saddle point. So what you see is this here has like a small, let's say, mass, which is the time scale at which you look at it, 1 over time scale divided by the Heisenberg time, so the frequency divided by the level spacing. So if omega divided by is large, then you can do a perturbation theory, but typically you are interested in effects where this becomes small and you have like these quantum interference processes. But then you see this term here will generate just a mass to both of the matrices. Only if they are identical, you will have again a Q squared equals 1, and this term drops out. So once you lock the two modes onto each other, then you end up with one random matrix that now describes a fully coupled system. And this is like a Boring limit. So this is like RMT of now a larger system. And the interesting part is like how this like coupling, the small coupling, then interferes with this time scale. Yeah.
Okay.
So and the saddles are here not so relevant. It's really about like, let's say, the soft modes, which at large coupling you immediately see they just get locked onto a single soft mode. Yeah.
Other questions? Okay, so maybe I can conclude with a quick question.
Yeah.
I mean, perhaps a spin-off of what you did could be the following. I mean, if I remember correctly, in the quantum sum model, let's say Lev and collaborators estimated where the critical disorder is based on the Fermi-Golden rule, right? Now you know at fixed n, or let's say at fixed g, which n you need in order to enter. So you might want to check which n should be enough to see numerically.
Yeah, I agree. I still have the feeling that the more interesting is if you really know about the distributions, because it's I don't know. I mean, like I agree, but it's still would be interesting probably to see like how the distributions are, and then I don't know. Yeah,
because I think you should be able to estimate the relevant n at which the numerics will agree with.
So is it correct to say that one of your predictions is that if you have a two-level system, the decay is not exponential? You can have a...
At long time, if you have a finite bath, so you already know that the exponential should stop at some value, which is like, well, if you have n levels to couple to a long time, you should not saturate to 0, but to 1 over n. And then the important thing is like the 1 over n, you can just think of a return probability to return, like you have n levels coupled to 1, you can, with a probability 1 over n, return to the one level you started from. And the important thing is if your bath is phase coherent, there's quantum interference processes which will enhance the return probability. And in the unitary class, they turn out to be very simple, and there's some semi-classical exactness behind, which tells you it's just like from second order perturbation theory, which gives you the linear ramp, which is why it's a spectral form factor immediately. In the other class, it's more complicated, but it's like the quantum interference correction to the return probability.
Yeah, okay. Yeah. So, but my question is, so you're predicting something that's not exponential.
Right, at long times.
Yeah. But then there's something called the quantum Zeno effect that also has modifications on the decay rate.
Yeah.
How can you distinguish between these two things?
I don't know to answer this question. Yeah.
Okay.
Yeah. It's a good question. It's
Because naively, I would guess that the quantum Zeno effect has to do with doing a measurement, with doing here is evolving without a measurement. So
yeah.
If you do the in the lab, you say not for this problem, but in the lab. Okay.
I don't know.
No. I thought you were talking about the theoretical situation. No, okay. I see.
I don't know. Yeah, it's a good point.
Okay, other questions, comments? Okay, if not, let's thank Tobias again.